Welcome to section 2 of reproduction. In this section, we'll be discussing important embryonic genes. This is the embryo overview image, which was discussed in great detail in the previous section. Right now, I just want you to focus down here on the fetus, and you can see that the fetus has these limbs. Now, several genes play a role in developing a normal limb. Let's dive into that now. This table lists 4 important genes. When you look at the left column, we've labeled these genes. But just remember that genes exert their effect through protein products. So for the remainder of the lecture, we will reference these genes, but keep the protein products of these genes in the back of your mind. So when we refer to fibroblast growth factor, or FGF, you should be thinking of the FGF proteins. Same thing with Wnt7, think of Wnt7 genes and the proteins. And sonic hedgehog, think of the gene and the proteins. When it comes to the Hox genes, it's important to know that these genes specifically produce transcription factors, and they have various names. So we'll just write TFs. So just think of genes and protein products, and when it comes to Hox genes, think specifically of transcription factors. Now let's dive into detail on each one, starting with fibroblast growth factor. Now FGF is responsible for limb elongation, and you can call that proximal distal limb development. An important note about this is that it's produced by the apical ectodermal ridge, or AER. This image shows the limb orientation, and it's growing outward like this, which again is done by FGF, and FGF is produced by the AER. And FGF specifically comes from the AER and acts in the progress zone to elongate the limb. So if you look at the key over here, FGF is responsible for proximal distal elongation. Next is Wnt7. This is responsible for dorsal ventral limb development. And just like with FGF, Wnt7 proteins are produced by the apical ectodermal ridge, or AER. What's interesting about the Wnt7 proteins is that its presence causes dorsal development, but the lack of Wnt7 leads to ventral development. So the apical ectodermal ridge produces Wnt7 proteins, and when these levels are high, you get dorsalization. So your arm looks like the back of your arm. But when it's lacking decreased Wnt7, you'll get what looks like the palm and the rest of the surface of your ventral arm. Now the last part to discuss is anterior and posterior patterning. We have 2 major genes that aid in anterior-posterior patterning, the homeobox or Hox genes and the sonic hedgehog genes. The easiest way to distinguish the 2 genes is to think of Hox genes as a gene important in creating body segments in the craniocaudal direction. For example, the Hox genes will indicate an arm should go here, and below that, you need to place the ribs, and then lower than that, you need to place the legs. And when it comes to the arm, the Hox genes will indicate you got to place an arm here, and you need 5 fingers here. So Hox genes indicate this craniocaudal direction, all the segments. So put a finger here, 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 and here. That will be dictated by the Hox genes. But when it comes to the sonic hedgehog genes, these will actually tell you what to do with those limbs that are made. For example, make this 5th digit really short so that it looks like a 5th digit. In other words, make it look like a pinky. So sonic hedgehog genes will say, make it this long, make it look like a pinky. So make it this long. This finger should be this long. This finger slightly longer than this one, and then make the thumb look like this. So those are all indicated by the sonic hedgehog genes. So as you can tell, Hox genes and sonic hedgehog genes are very important. And if the Hox genes or sonic hedgehog genes are messed up, you can get some weird problems. For example, with Hox genes, if there are mutations, it can lead to body parts in abnormal locations. Most commonly, patients get polydactyly or syndactyly. The image on the left shows an extra finger, or 6th digit, and Hox genes are responsible for craniocaudal patterning. So cranial being here, and then caudal being down here. So it made the mistake of saying that there should be this extra digit. So this would be called polydactyly. The right image shows fingers that didn't separate as they should have. This is called syndactyly. Now Hox genes normally dictate that this limb should separate into 5 digits, but the segmenting was messed up somehow. So there's only 4 digits. Now let's move back to sonic hedgehog genes. One thing we didn't mention before is that sonic hedgehog genes are responsible for separating the forebrain into the right and left hemispheres. This picture was described in the neurology embryology section, and as you can see, we have the prosencephalon here, and it forms the forebrain. It begins as a single mass, but it eventually becomes a right hemisphere and a left hemisphere. And the sonic hedgehog genes are responsible for this. That means that if there's a mutation in the sonic hedgehog gene, the patient can get holoprosencephaly. This slide is also from our neuroembryology chapter, and this depicts holoprosencephaly, or lack of separation of the forebrain's left and right hemispheres. And you can see that there's a variety of presentations. And when this occurs, you can understand that there's CNS problems, developmental delays, you can have one eye, there's all kinds of problems, many of which are incompatible with life, but can also be pretty mild, as you can see down here with image E. Now let's do a question to apply what you've learned. A baby is born with forearm flexor muscles where extensor muscles should have been. This abnormality was most likely caused by undersecretion of a molecule normally secreted from which of the following? A. Zone of polarizing action. B. Apical ectodermal ridge. C. Progress zone. D. Mesoderm. Or E. Endoderm. Now we know that forearm flexor muscles should be on the ventral surface, and the extensor muscles should be on the dorsal surface. However, instead of these extensor muscles, these forearm flexor muscles are on the dorsal surface. In other words, there's ventral anatomy on the dorsal surface. We call that abnormal ventralization of his arms. And since we're dealing with ventral and dorsal patterning, ultimately we should be thinking about dorsal ventral patterning. What gene and protein are responsible for dorsal ventral patterning? That would be Wnt7. And this protein is secreted from the apical ectodermal ridge, which is choice B. Going back to this table, we see that WNT7, Wnt7, is produced by the apical ectodermal ridge, and it's responsible for the dorsal ventral limb development. Now, A and C are wrong because these are zones that are responsible for producing proteins that have other impacts in limb development, not dorsal ventral development. For example, the progress zone releases FGF and aids limb elongation. And D and E are incorrect because we know that the apical ectodermal ridge is ectoderm, which is right there in the name. So Wnt7 protein does not come from mesoderm or endoderm. And that concludes this section.